All right, guys. So for those who are watching the video, I'm so sorry. I just pressed and recorded this, but pretty much I just introduced or what is to be expected in the exam. Feel free to open your notes or have it with you. It's better, or really highly recommend to have a physical copy of your notes and your formula sheets with you while you're taking the exam. We are to be on Zoom when you're taking the exam. You will be given bonus points if you are on Zoom. In fact, you cannot take your exam if you are not on Zoom, because for you to open the quiz, there is a code there, and I'm gonna post that on Zoom. Okay, we still have our phones to show our desk view while doing the exam. Will we still have to use our phones? You don't use your phones. Okay, we only use the phones when we have a Kahoot game, or we're needing to have an external device to answer. But you won't be needing that. So it's pretty much your notes and then you going to Canvas to open the quiz. And while you're doing that, you need to be on Zoom, and you turn on your cameras. So does that make sense, guys? Kind of like what we're doing here. We're zooming right now, but you can actually go externally and then minimize that Zoom file of yours, and then you can just work separately, right? You can actually multitask right now. Any questions with regards to the exam?
I have a question.
Yes, go ahead.
So for when we're doing the exam, do you need to see our workspace?
No, absolutely not. Yeah, so you just turn off have your microphones muted, but you just have to turn on your cameras, okay? And make sure that your entire face will be shown. So it's not just like this,
Okay.
okay? So I want to see the entire face, basically. If a majority of you will not do that, I might be forced to use Proctorio, and there's mixed feelings about Proctorio. Somebody likes it. I mean, Folsom really have no problem about that, but then some people don't like it, and I just have a feeling because they can't use. Um, I don't know. It is what it is, right? So um, we're going to I'm gonna give you free access to the world, but I want to see your work. If there's calculations, I want to see your work. So there might be a few of that, okay? And there are some things that are not Googleable. I just have to tell you, when we create these exams, these are really hard ones, and this is not hard ones, but these are really ones that you need to know, and you can't just search the question and you'll get the answer. So with that, we're gonna have to get started, and let me just close my video here for a bit because I need to grab my pen. So this right here is a question on your homework, and we can answer that together. Let me see if I can find my tablet. Oh, oh. I always say that we have in the house, we have a little friendly ghost who tries to play tricks on us because now I can't even find my pen. Okay. So I hope you guys know how to do this. If not, we will learn how to do this. I'm just going to go over and review a few things. And like I said, this is really a free fall for all any kind of questions that you may have with regards to quiz, homework, anything. We're going to go over it today. But there is a video that I want for you to watch on, aside from the ones that I assigned or posted on the module, that will be included on the exam. All right. So just think of transaction. Okay. So say for instance, I want to buy your phone. Okay. You're the seller. You're willing to sell me your phone for $100. I'm a willing buyer. The problem is that the currency is different. So say you want it in $100. I only have my money in pesos. So there's two ways for the transaction to occur. I could either convert my pesos to dollars and give you the $100, or you would be more than happy to convert that $100 to its equivalent pesos and be willing enough to accept my pesos. Okay, so it's still $100. The amount is still that. It's just the currency is different. Okay, same thing holds true for this type of problem. When you have your density question, not all the times the density information will be the same units as the I'm sorry. No, you do have a homework. It's not assigned. Okay, I'm gonna have to check on that, Kendall. Let me get back on that, okay? Okay, sorry, let me just read a few more things here on the scroll. This can be study guide. I will give you some study guides if you want more practice stuff. But for those who came in late, like I said, you can always practice on the study module that is found on your Mastering Chemistry. How do we open Canvas and take the quiz while being on Zoom? You can actually do that. So you just have to minimize your Zoom screen. And you can practice doing that now if you want. You can minimize it and go to your Canvas. When we upload the work to exam on Canvas, is it okay if we take pictures of the work on our phones? That's how I think it's the fastest way to do it. Is you write on a piece of paper, take a picture using your phone, and then upload it to your Canvas. Now, if you have your Canvas app on your phone, it's actually faster because you can just upload and submit your work through that app, rather than sending it through an email, downloading it to your desktop, and then uploading it to your Canvas. I'm going to check on the homework, Kendall. So let me get back to that. And if I forget, please remind me. All right. So let's get to this problem. And I hope you have seen this. Well, my chat box was there. So the density information here is in grams per cm cube. Okay. Oh no, I hate this. This just slows me down. The information, we know that density is always mass as a function of volume. So you guys prefer to just plug it into this equation, and that's fine. But remember, if you're plugging in information into an equation, make sure that it's analytically correct. The units of mass must be grams, and the units of volume must be in cm cube. Okay, so that's one way of solving this. If you take a look at the mass is given in kilograms. So you need to first convert it so that it's grams. Once it's in grams, then you can plug it into the equation. Then the only unknown there will be volume. But know that the volume that you will get in this equation is in cm cube. The volume that is asked of you is not in cm cube, but rather you're asked to find the equivalent deciliter of that volume. So once you get this, plug it into the equation. And to the equation in order to get the volume in cm cube. And then the third step is to convert that volume into its equivalent deciliter value. Okay, that's one route. The second route is to convert the density information from grams per cm cube to kilograms per deciliter. If you convert it that way, then you can just plug in all your informations as is. So you put in your mass there, the 4.39 kilogram, and the unknown that you will have there, the volume, it's gonna be in deciliters already, okay? Kind of like the transaction. I could either convert my pesos to dollars, or it could be that you'd be fine accepting the pesos and getting it in a peso form. Okay, the money in peso form. Okay, so it's really up to you guys. And I think if you're not comfortable with the dimensional analysis, the train track, wherein you have to manipulate the numerator, and then after you've manipulated the numerator from grams to kilograms, then you manipulate and then change the and convert the units of the denominator from cm cubed to deciliter. Okay, if you're not comfortable with that, then by all means do this first route. Okay, just please keep a mental note of the units. And that's why I always like my students to, as a practice, to whenever you're doing some calculations, always don't have naked numbers. Just put a unit in there, because you are dealing with a bunch of units, and it can get easily confused if you don't put a unit in there. Okay. So I hope that makes sense. So how to convert kilograms to grams? Do you guys know how to do that? So we know that a kilo, and guys, I really need, oh, wait. I really need to find my, I'm pretty sure it's real here somewhere, but give me a second, okay? So I want you guys to work on that. And let me see. There's a few things that I want you to work. So maybe we should go with our breakout session. I'm gonna put you in a breakout session so you guys could work on this together as a group. And I want to open out, okay, so if you go to your Canvas right now, so this will be our practice. You go to your Canvas right now, I'm going to open this one. Okay, I'm gonna open this discussion breakout session. If you download that and open it, what you will see is another problem. Okay, so if you, once you solve this density problem, I want you guys to continue and try to solve this calculations, this energy calculations. Okay, so let me divide you guys into groups. And I'll give you about 5 minutes to work out the problems, okay, or 5 or 6 minutes, so 3 minutes per question. So that's the typical amount. So we have, let's get you into more 23. Okay, so 2 people. So stay in the breakout room, and then I'm going to close everybody after 6 minutes. Okay, work on these problems, the breakout session, this problem, and then the density question. All right. Can you really? I know. I'm so sorry. Let me find my tablet, my pen once we have that. Okay. Okay. All right, so we're waiting for a few more people to get out of the room. Okay, all right, perfect. Okay, guys, so I hope that was meaningful for you guys and you were able to talk it with your group. Now, how much did you guys get? And before we do that, tell me which one works for you. Is it better for you guys to convert the masses and the volumes first before you, or the mass first before you plug it in? Until 2. What's until 2? I'm sorry, Paulina, I just got until 2, so I don't see the full length to this. All right, so I'm gonna work on the problem and let me know if you have the same one as well. Okay, but first let me know which one you guys prefer. I think we only got to problem number 2. Okay, so we were able to do the which one? Were you able to do this density question first, or did you do the energy calculations? You only did the energy calculations. Okay, that's okay. We will do density first, and then we're gonna move on to calculations. Why not? Okay. Confused on finding the density. Okay. Oh, okay. Okay. I see what you mean. Okay, so I have the density here, and I'll probably post that on the discussion PowerPoint slides as well. Okay, so I'm gonna do the usual route wherein students like to do plug and play. They want to use this equation instead of converting the density into its corresponding masses and volume. So we'll do that, okay? The mass has to be in grams, and the volume that you will get in this equation is going to be in cm cubed. The information, however, for the mass is in kilograms, and so I need to convert kilograms to grams first. So this is just for mass info. So as you know, density is actually a function of 2 units. It's the weight of your object with respect to its volume, okay? And you may have the same masses, or 2 objects may have the same masses, but they can have different volume. 2 objects can have the same volume, but they may weigh differently, okay? So if you take the ratio of these 2, mass over volume, the value that you will get is called density. And this density is really unique to that particular object. So 2 objects may look alike, they may look gold and shiny in appearance, and yet one might weigh heavier than the other. If we take the ratio of this, and if you will get a certain amount and you compare that to like the density of gold, that's how you can figure out whether that's fake gold or real gold, by measuring the density and not by how it looks like or by the volume alone. Okay, you have to take the ratio of the 2. And so this unit is very, very important. This is also the reason why when you go out and measure the samples or the pollutants in your waste water streams, like river, lakes, so on and so forth, you want to calculate the pollutants, you don't take a whole bucket or you don't empty out the river. You only take a sample of that, and that sample and that concentration is basically the same concentration whether you take a pail of water or 2 pails of water into your lab. Okay, so density is important. Okay, so we convert kilograms to grams. The iron is given in kilograms. To plug it into the equation, we have to convert it into grams, okay? So density is equals to mass over volume. You're given the density value, that's grams per cm cube. You plug the mass in grams, but since it's not in grams first, I'm going to go and convert it. So 1 kilogram is 1,000 grams. I know that from the prefix kilo, okay? Kilo means 1,000 times of the unit. So I got 4.39 times 10 to the power of 3 grams. Now that the mass is in grams, I can then plug it into this equation up top. The only unknown there is the volume. That's the one that we are asked to solve. Okay, so this is going to be, you just do a manipulation. Remember, if the volume is in the denominator, we want to isolate it from the rest of the numbers that's found on the same side of the equation. And to do that, we can move it to the left side of the equation. And anything here on the left, we need to bring it to the right side of the equation. If it's found on the numerator, you bring it down as a denominator. Okay, so 4.39, if you divide that by your density, what I have here is 558.52, bunches of numbers in there. I'm just gonna chop this number all the way to 4 decimal place, okay? So there's a whole stream of numbers in there, but let me just keep that to 4 decimal places over. Now, notice that the volume here, what's the unit of volume here? The volume here has to correspond to the volume of density, and that's cm cube. So the volume that you will get here is in cubic centimeters. The numbers here have 3 sig figs, so your final answer should be in 3 sig figs, right? But this is not your final answer. In fact, this is only an intermediate answer. We still have a way to go. You're not asked to find a volume in cm cube, but rather you're asked to find a volume in deciliter. And so that's why I'm not rounding it off, because as you keep on rounding off along the way, you're going to introduce some errors. Okay, it's not going to be accurate. So I'm just making a bar here to remind myself, like, hey, I need to round it off to 3 sig figs, or you could write 3 sig figs there as a reminder, so that eventually once it's converted to deciliter, all you need to do is just convert it to 3 significant figures. So now the final step is to convert the cm cube that I got from the equation to deciliter. I know that cm cube, 5242 cm cube, cm cube right here. Sorry, let me just scroll this up real quick. cm cube is actually equivalent to 1 ml. We established that, right? That's 1 cc. 1 cc is equivalent to 1 ml. We also know that 1 milliliter, the milli means it's a 1 over 1,000 of a liter, or 1,000 milliliters contains 1 liter. We also know that a deciliter means what? What does deci mean? Anybody?
To the power of -1.
Perfect. Okay, so it's to the power of -1 of any base unit. And in this case, the unit is liter. Okay, I'm going to make use of all of these mathematical statements in my dimensional analysis to convert one from the other. And of course, in order to go from cm cube to deciliter, I need to first convert it to milliliters, and then to its base unit, and then from base unit to its desired unit, to deciliter. So each of these arrows represents a train track or a conversion factor that's going to be used. So I'm going to start with cm cube 2 ml, putting cm cube at the denominator. That way it will cancel with the original unit. Now that it's in milliliter, my next step is to figure out a link or a tie or information to tie in milliliters to liters, and that's this one. And then finally, deciliters to liters. So 1 times 10 to the negative 1 of a liter is equivalent to deciliter. Okay, now all you need to do is multiply everything on the top and divide it with everything that's found in the bottom. And what you will get there, sorry, it is, yeah. Divided by 0.1. And I got 5.58524 something something deciliters. Let's round it off to 3 sig figs, dropping the rest of these digits that's trailing. Notice that the first digit here to be dropped is 5 and up, meaning to say it's, if you just cancel that out, it's going to, it weighs something, okay? You need to add 1 more digit, okay? For numbers that are 4 and below, they are not important enough to weigh everything, but to just discard 5 to 4, that's significant. And so don't just ignore it. You have to consider that there's bunches of numbers that you are chopping off. And in order to do that, you have to add 1 digit to this last retaining number. Okay. So discussions are actually recorded, and I usually, at the end of this discussion, I usually let it process in a cloud. Once it's ready, I usually grab that link and then I link it to Mastering not Mastering Canvas, to our Canvas. So if you go to our Canvas page, it'll take a while. So I usually just let it wait for like 2 hours for me to do it or upload it. So if we go to our Canvas page under modules, if you notice, it's actually right there. So this was from last week's, and on week 1 it was an orientation, so I posted week 1. Okay, so you're gonna see these recordings actually for discussion sessions. Alrighty, so that's it for density, guys. And it can be anything. I could basically ask you for the mass, or I could even ask you for the density. And if you notice, it's actually harder if you're asked for the volume. That's because you have to do some algebraic manipulation. It's not quite easy as just ask for the density if you're given mass over volume. And so just be aware of this. You can just use this same problem and then try to solve one. So you're given all of these information, try to solve for, say, density, or try to solve for, say, mass, okay? And so you can find yourself, and once you're savvy with this, you'll basically see that it's actually repetitive and it's just the same. I could ask you, instead of deciliters, it could be centiliters, or it could be milliliters, or it could be megaliters, okay? So that's the only difference with the problems, but pretty much the structure is the same. Let's try to solve the one that is in the breakout session, and that's your heat equation. So we're given the mass of an unknown substance, so mass is given. Remember, our heat equation is always Q is equals to mc delta T, where these 3 refers to the mass of the object, the property of the object called specific heat capacity, and the temperature. So what's the original temperature of the object, and then how far do you want to heat it up, or what's your desired temperature, or if you want to cool it down, what's the final temperature. So all of this comes into play, and that's the amount of heat that you will need to either add or remove on your system. So let's see, mass is given, that's 15.75 grams. The substance is unknown. Not much information is given. We are given the heat. It is releasing this much heat. Okay, so it's giving off this heat, meaning to say it's going out of your system. So it's negative. If the heat is coming in, then that means your object is absorbing the heat. If this is releasing the heat, that means it's negative, it's coming out. The way to do that is to mathematically express it by a plus and minus sign, if we want to put that into the equation. So now let's take a look at the other information here. The temperature change from 175. So the original temperature was 175 degrees Celsius. And if you really think about it, if your object is losing heat, the temperature is going to drop down. The temperature went from 175 to 25 degrees centigrade. So that makes sense. You're asked to find the only unknown here, which is the C, the specific heat capacity for this substance. So if you could do it a number of ways, you could already plug this information into this equation, or you could rearrange your equations first and then plug in data later. And I hope you know how to manipulate the equation. If you're trying to solve for one parameter, say in this case C, you want to move the rest of the parameters on the other side of the equation. If it is found in the numerator, you bring it down. Okay, it becomes a denominator. So M and delta T becomes a denominator on the other side of the equation. Now that we have that, then all we need to do is just plug in those information. And that's it. So C, heat is negative 5468 joules divided by the mass, 15.75 grams, divided by the change in temperature. The delta sign means that it's always final minus the initial temperature. Okay, so final temperature is 25. Subtract it subtract it with the 175 degrees Celsius. Notice that this value is going to make it a negative, but you don't have to worry because this numerator part is also a negative, so that just cancels the negative sign out. And in fact, specific heat capacity is always positive. You're comparing two objects' property. One may have a lower value, which means to say that it heats up and cools down much quicker, and versus another object that has a really high specific heat capacity. So plug this into your equation, and what you will get you're going to have the units joules divided by grams degrees centigrade, and that's the unit of specific heat. 5468 divided by 15.75. And I want you guys to give me your answers here, or verify my value. So 2.31449, is that our final answer? Okay, it has to be a positive value. Okay. Because this denominator 25 minus 175 gives you negative 150. Now let's take a look at sig figs because we need to process our work, right? 5468 joules has 4 sig figs. 15.75 has 4 sig figs. If you subtract this, you're going to get negative 150, and it's accurate to the ones place. This is ones. This is ones. When you're subtracting things, you're looking at the decimal place, so ones place. So 443 sig figs, you need to round it off to 3 significant figures. That's how I got that number. Okay, you can't have an answer that is even more precise than your data's. okay? So it has to have the same accuracy and precision. Okay, so what does this tell me? Okay, just as a bunch of reference here, okay? So we know that the specific heat capacity of water has 4.184 joules per gram degrees Celsius, meaning to say if you have a gram of water and you want to change its temperature to 1 degree, you're going to need to heat it up to 4 joules of energy. Usually metals will have a lower heat capacity that's around 0.9 or less than 1. No, calories, so that's less than 4. Less than 4, so around less than 3 joules per gram. That's the typical amount of heat. So this will give me an idea that this is probably a metal. Okay, it takes it to cool down very much quicker. So imagine this: if you have a piece of metal versus water in the ice tray, okay, and you want to stuff that into your freezer, you're going to notice that, or kitchen knife, okay, so if you notice that your kitchen knife is actually going to get cooler much faster than your water, okay, that's because of the specific heat capacity of water. It takes a while for the freezer to remove that 4 joules of energy from water. Whereas for metal, the freezer only needs to take this much of energy, and then the temperature is going to drop down. Same thing holds true if you're trying to heat these objects up. If you have a pail of, let's say a cup of water, okay, versus a metal, your kitchen knife, and you want to put that out in the driveway, you're going to notice that your metal's going to heat up much faster than water, because you only need this much of heat that is radiated from the sun in order to elevate its temperature up by 1 degree. So that's what specific heat capacity is very important when we're trying to analyze 2 or more properties. And you would see that back in the day, they use metals as implants to replace a bone fracture, so on and so forth. But the problem with metal is that the beauty about metal is that, number one, it's hard, it doesn't crack easily. So when you put the metal in there, implants, they're really there, right, for a long run. They're very sturdy. The problem with that is that it has a different specific heat capacity. It cools down much faster and it heats up much faster. So during winter time, a lot of patients back in the day complains about the gnawing of the metal in their limbs or wherever they have those implants. And that's because of that issue. And so nowadays, with the new technology, they have created plastics in lieu of metals, so that doesn't cool as quicker, doesn't heat up much quicker. And not only that, they're more biocompatible. So metals, the cells that surrounding the metals, they would see some foreign objects in there and they're try to defend themselves, right? So there's lesser impact to the body when it comes to that. Okay. Perfect. Everybody is now, how many sig figs do we have as an answer? Okay, you always have to look at your data. And if you notice, the only tricky part here is the temperature. When you're subtracting the temperature, you're doing subtraction, and you have to remember the rules of subtraction. You don't look at the sig figs, you look at the decimal place of the number. And so if this is 25.0 minus 175.0, then this number would have been accurate to the 1 decimal place. And then when you're multiplying everything and dividing everything, then you're going to look at the significant figures, because that's the rule, right? When you're multiplying or dividing, you're looking at the significant figure. This data has 4 significant figures. This data has 4 significant figures. This data is accurate all the way to the 1 decimal place, and if you count the significant figures, that's going to be 4. So the final answer for that particular problem would have been 2.314. Okay. Speaking of which, guys, if you go and scroll under module 3, you're going to see exam study guide materials, and there's some stuff there to help you with significant figure problems. Yes, go ahead. Question. Why did the release become negative? Yeah, so that's how the thing with heat is that we can't, how do you mathematically explain that the heat is coming in and it's absorbed in the body versus heat is coming out of the body? The only way for you to do that is to mathematically change the signs. If it's plus, then that means your object is absorbing heat. You're heating it up in the driveway. If you stuff it in the freezer, you're removing heat from the object, and so it's going to be heat coming out. So it's going to be negative. Think of money when it comes to that. When you put money into the bank, it's going to be plus on your account. If you withdraw money, it's going to be negative on your account. I like to think of everything with money because I'm like, oh, I like to look at not that. Okay, that's bad. It's all recorded. It shouldn't be said that way, but you know what I mean. It's easier to think about that. You don't never want to shortchange yourself. By the way, guys, this is also another review I posted on the exam study guides. Questions like this could arise in the exam, so I want you to go over the questions and try to answer it yourself and look at the answers. Okay. All right. So, to follow up question, calculate the final temperature if it absorbs heat. Okay, this is actually nice. Let me get this 2 questions. Let's plug that into this. All right. So notice that the question is actually very similar. So we had the first one, we had the specific heat capacity to be 2.31 joules per gram degrees centigrade. Was it 2.31? Okay, okay. All right. And then, okay. So here, take a look at number 1 and compare that to the number 2 question. So here you're using the same object, but this time around you're trying to heat the object up, okay? So calculate the final temperature if it absorbs heat. Is it higher or lower than the initial temperature? So what does our temperature object looks like? So we know for a fact that it has a mass of 15 grams. Okay. We know for a fact that it's originally at 175 degrees centigrade. And then when we cool it down, its temperature dropped to room temperature. Okay. And this question actually is pretty vague because what do you mean by that? Are you talking about from 25 degrees, from room temperature? Are we going to add heat? Very, very vague right there. Okay, so let's just make up our own problem then. This is such a vague question. Okay, so let's have the same problem, 15.75 grams. Instead of releasing heat, let's have it absorb this much heat, okay? And let's figure out what's the temperature of this object. Okay, so Q is equals to MC delta T. If you're absorbing heat, it's gonna be positive value. The mass didn't change, it's still 15.75 grams. The specific heat capacity of the object is already calculated from the first problem. We have identified this object. So let's try to have the initial temperature. Okay, let's still have our starting point 75. Now we're asked to find for the final temperature, okay? So remember, delta change is always what you start, is always final minus initial, okay? That's what change means, or the delta sign means. So final temperature is unknown minus the initial temperature of 175 degrees Celsius. Okay, so notice how this is being phrased. The only difference that is the sign is changed, right? Okay, so let's manipulate everything. I actually kind of like to manipulate the equations first before I plug in my equation. It's easier for me to see it, but since we've already put in our data, that's fine. Okay, specific 2.31 joules per gram degrees Celsius. Notice here that the grams cancel out, the joules cancel out, and you're only left there with the units of temperature, which makes sense. Final temperature is TF minus 175 degrees centigrade. So if you add both sides of the equation with plus 175, you will get rid of this 175 here in the equation, thus solving for the final temp. Okay. All right, so that's how I would do this. 175 plus whatever you got from this calculation. And let's just do that already. I got 150 something here, plus 175. So my final answer is 325 degrees centigrade. So it got hotter, which makes sense. If you're absorbing more heat, your temperature is going to get elevated more and more. So let's see, we have 4 sig figs, 4 sig figs, 3 sig figs. This would have been accurate to 150. When you add it to this one, you're looking at the ones place. That's why I'm rounding it off to 325. Okay. How did I get, okay, it's from this one, from the heat divided by the mass and the specific heat. So 5468 divided by 15.75 divided by 2.31, I got 150. But please correct me, I might be wrong here. I need someone to verify my calculations. Awesome. One concurred, Matthew Chong concurred, and so I'm gonna move on. Okay, kind of like, if you know Catch Me If You Can, do you concur? I love that scene, do you concur? Leo DiCaprio was like, do you concur? He doesn't know anything new. So let's move on, guys. So one thing in the recording, and I hope you've already watched the pre-recorded videos, was it's now, chapter 1 is really more of the math part. Once we know the math part, we just set that out for a bit, and we're gonna call on that later on when we go to chapter 5. Now we're digging deep. We're gonna get to know these elements and whatever make up our substances. So there is a video there wherein you are asked to categorize matter. Is that matter a pure element? And the only way for you to know is that you bust out your periodic table. If you can find it there, it's a pure element. Now, water, is that an element or a compound? And you'll say it's a compound. It's made up of 2 hydrogen atoms and 1 oxygen. So if it's made up of 2 or more, it becomes a compound. Okay, so element, lithium, for instance. It's an element. This is a compound. All right. Now we can mix and match two elements and two compounds together in order to form a mixture. Okay, so say for instance, I'm going to put sand, silicon dioxide. That's a compound. It's made up of silicon and 2 oxygen atoms. I could put sand in water and I'm going to create a mixture. But this sand mixture is called what? Okay, so there are 2 kinds of mixture. It's either homogeneous mixture or heterogeneous mixture. Hetero means that you can actually see 2 things. They're not uniformly, there's no uniform appearance. Obviously, you can see sand settling at the bottom and water on top. So that's a hetero mixture. An example of homogeneous mixture, right, that I mentioned in the video is ice cream, vanilla ice cream. It's made up of what? It's made up of sugar, milk, water, vanilla flavor, but you can't really isolate and figure out, oh, that right there is water, that right there is the sugar, right? They all will appear into this one creamy, yummy white stuff that we call ice cream. And so that's a homogeneous mixture. So at least I want you guys to identify, if I'm going to give you several objects found in nature, and basically be able to identify whether it's a mixture. And if it is a mixture, what type? Is it heterogeneous or homogeneous? If it's a pure substance, then you need to identify whether it's an element or compound, okay? In that video also, we talked about ions. We've introduced ions or components in an element. So element is made up of atoms, and atoms is comprised of 3 subparticles. So we have your electrons, neutrons, and who can tell me the last one?
Protons.
Protons, awesome. So if we go and look at our periodic table, okay, the number here on top tells you one thing. It tells you the number of protons that's found in that atom. So if we go and look at, say, silver, silver has 47 protons that's found in the center of its nucleus. Gold has 79 protons, and protons are positively charged. And if you notice, if you just add one more proton and embed that into the nucleus of that element, you will create a new atom, a new element. And that's what physicists are doing. Physicists. 150. Okay. Okay. So that's what physicists are doing. If you add, they're trying in the lab, Berkeley's one really good lab right here in California. They're trying to create more and more elements by adding that proton into the nucleus. It's not very easy because most of them, once you go past this numbers right here around the 80 portion, it's kind of really unstable. You can have some sort, what we call as nuclear decay. Exhibit some radiation, some sort. So that's their own arena, and it takes them a while. Whoever can get a very stable atom can get to name their element. That's pretty cool and fascinating in their field. And I am not really fascinated by that, but for them it's probably pretty interesting. Okay. So there you go. Now atoms, if it's a neutral atom, we said that atoms right there, we said that protons carry a charge of positive, right? Okay. And we take a look at an element there. We had our example real quickly was our silver. It has 47 protons in its nucleus. So this is your nucleus. That's way inside your atom. There's 47 charged particles there called the protons for silver. Okay, if you have a neutral element or neutral atom, then the number of protons, electrons that's surrounding this nucleus will also be 47 particles. Electrons are the ones that carry a negative charge, okay? So negative 47 plus positive 47, that would just be 0 or a neutral atom. Now, what they notice is that when they weigh this atom in a pseudo scale, if you weigh an atom, you're gonna measure more each of this. Let's take a look at the weight of these particles. Protons roughly weigh 1 atomic mass unit, and this 1 AMU has a corresponding mass in grams. But because it's so light, we never use grams, and it's in the power of negative 27, right? We only use AMU. So it will have a weight of 1 AMU. Electrons, on the other hand, relative to these protons, they weigh nothing. They're like cloud of electrons. So imagine trying to weigh a cotton on top of a calculator. You just ignore the cotton because the cotton weighs pretty much nothing, and most of the weight is from the mass of your calculator, right? So what they notice there, it actually doesn't weigh 47 AMU. It weighs more. So they're thinking there must be other particles there that's not just electrons and protons. It must have a substantial weight, but it doesn't have any charge, and that's your neutrons. Okay, for silver, in the periodic table, you cannot see the weight of your neutron, okay? Because a silver atom may have more than different neutrons in them, okay? But we can roughly approximate how much a neutron is. So if everything adds up to 108, 47 minus 108, we have a general idea that majority of the silver atoms will have 61 neutrons, roundabout. (61 neutrons that doesn't have any charge. Alrighty. So when you write it out, this is the way we would write it out. We will put the number of protons at the bottom, lower subscript. So that's 47. And we will put the thing that is found in the nucleus. What are the particles found in the nucleus? Your protons and the neutrons. The overall mass population. If you add it up, if this is election, we're gonna take a poll. 47 plus 61, that's gonna be 108. You're gonna put that number on top. So the top number here is always a bigger number compared to the bottom number. The top number refers to the number of particles that's found in the nucleus, and these are your protons and your neutrons. The bottom number here refers to your protons. Therefore, if you take the difference of this, 108 minus 47, 61, that's the number of neutrons present in your atom, okay? We call this the mass number by the letter A, or designated by the letter A meaning all. I'm just making that up, guys. It's just designated as A, and I'm saying it's all, versus the number of protons, which we call as the atomic number, with a designated symbol Z. And this is why students get confused about it, because when I ask what is the element with an atomic number 47, they would say silver, right? But if I say, what is the element that has A equals to 47, they would think that it's silver. If the mass number is 47, then it's a different element. Okay. It's possible to be titanium. 22. Oop, 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 oop. 22. And that's your titanium. So if you're given these symbols, please make sure to know what is A and what is Z. Always look at the lower number. That's usually the number of protons in there. And then in the periodic table, this is also another thing that students get confused on, because this number in the periodic table, so this is our symbol for silver. In the periodic table, this 47 is written on the top portion of the periodic of the element. Okay, so this top number refers to the atomic number. The number at the bottom there is the weight of the atom. Okay. And I'm gonna do one more, guys, before I'm gonna let you guys go, because like I said, there is a video and I think I've already posted. You should be able to see it already. Under modules, you go to module 3 because it's week 3, and you may want to watch this. I'm gonna put this way up here so that you'll know that it's part of the examination. Okay, so module 3, periodic table. It's about periodic tables. Okay. In a periodic table, let me just segue it for a bit here. We're going to talk about periodic table. So during the test, I might ask you to find an element by the locations in the periodic table. So I might say the following are elements in the halogen group except. So you need to know what halogen group is. Okay. And in that video, it's gonna explain you what they are, and they're right here. So I'm gonna give you several elements, and you're gonna have to identify which one is not a halogen group. I'm also gonna ask you, okay, what is the element that is in group 3A and is in the second period? So group number and period number are different. So group number is the columns. So you notice if you count this from left to right, you're gonna notice there's gonna be 18 groups. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We hardly say group 8, number 13. Sometimes we just say group 3A, okay? So that's another way of saying it. And when we say period, we're looking at it by rows. So this is period 1, period 2, period 3, period 4, period 5, period 6, period 7. So when you say period 2, group 3A, then we're talking about boron. Okay. So please watch that video because there might be other stuff that we're going to be talking about in that. That's going to be included in the exam. Okay, isotopes. When we're talking about elements, we said elements are made up of atoms, okay, little tiny atoms. And these atoms contains little subatomic particles, kind of like eggs. Eggs contains egg yolk and egg white, okay? So an atom can contain many particles, but without one, it's not going to function perfectly. So kind of like the cells in our body, our tissues, our muscles, they are all made up of cells. That's the smallest living unit. The cells may contain other parts, but if you take out, say, a portion of that, that cell will no longer function. It's going to die. So all atoms are like that. The thing with atoms of the same element, for instance, in this case, rubidium, Rb, draw. Rb, rubidium. A rubidium atom, if we look at the periodic table, we can find a rubidium right here on the group 1. It's the 37th element in the periodic table. The thing with the rubidium is that it can actually, different rubidium atoms can actually weigh differently. Kind of like if I'm going to measure you, you will have a different weight than me versus your classmates in this Zoom class, right? We all have different weights. If we take the average, or if we count or figure out how many of you are of this particular age, how many of you are female, if we take the average, we will have an idea of the average weight of a typical 18-year-old female students in Chem 305. Okay, so that's the average weight. But you could either be higher weight or your weight could be lower than the average. Same thing for our atoms. Rubidium atoms can have different weights. So if you take a look at this one rubidium atom, this rubidium atom has a weight of 84.9 AMU. Contrast that to another rubidium atom that weighs around 86.9. Okay, so these rubidium atoms weigh differently. They're still a rubidium atom because they have 37 protons in their nucleus. What changes with their weight is because they have different neutrons. So if you have the protons, neutrons, electrons, they have the same number of protons, 37 particles inside the nucleus. The only difference is that they have different neutron amounts. One is obviously have more neutrons than the other. So it's rubidium 87 that is heavier, a little bit fatty, on the fatty side, right? This rubidium. And so we're gonna take the average weight of this, and that will be a good representation of what rubidium will weigh. So that's a good representation. So that's the average weight. So how do we do that? So kind of like taking the test. It's a weighted average. So weighted average, we have to figure out how many rubidium atoms weigh 84.9. 72% of the population weighs 84, while the remaining 30% weighs 87. So most of the rubidium atoms weighs 84 AMU. So you would expect that the average will basically represent on who is the majority, right? If most of them weighs 84 on a leaner or skinnier side, you're gonna assume that your average weight is around that number, 85 versus 87. If I round this off. So I would expect that it's closer to 85 than 87. So how do we do that? We need to multiply this abundance by the weight and add it to the contribution of rubidium 87. Now notice that I converted it into its decimal form, because this is percentage, and you have to move the decimal places 2 places over. 9092 AMU. Okay, So this is the contribution of rubidium-85 atoms. This is the contribution of rubidium-87 atoms. And if we take and add them together, you're gonna get close to 85. What do you get there, by the way, guys? What number do you get? How much do you get? So that's the thing. Let's use our calculator, and I hope you know how to use your calculator. If you haven't done it, do it at least once, because you will notice that if you plug it differently, or if you don't know how to use it, you might end up with a different number. Okay, I got 100. Oops, that tells me that I'm wrong. I'm gonna wait for you guys to give me the answer. 85.4681. Thank you so much. AMU, right? It's closer to 85 than 87. That makes sense. Now, if we look at the periodic table once more and locate rubidium, you're going to see that number at the bottom, 85.47. This represents the average weight of rubidium atoms. Okay, that's why you don't see the neutrons present in there, but what you would see is the average weight of the rubidium atoms. So that's that number. So now the question is, okay, so if that number is on the periodic table, why do I need to learn this? All I need to do is look at the periodic table, right? Correct. But sometimes I would not ask you to give me the average weight. I might ask you the reverse. I might ask you, what is the weight of rubidium-85 if you have this information? Okay, you have to work your way backwards, and you need to know how to do that. So another thing that I would like to highlight here is, what if I'm not going to give you this information? I need a darker color to erase that. Okay, and then what if I'm not going to give you this information? And then I'm going to say, okay, solve for the atomic mass of rubidium-85 if these are the only information that you have. So we know the average weight is 85.47 from the periodic table, right? We know that this is 72%, so we got that. This is the unknown. This is the one that we're trying to solve. This is X, okay? We know 86, it's given, but we don't know this number. How do we get this number? It definitely. So notice percentage is, it must add up to 100. So if the information here is not given, just subtract 72 from 100 and you're gonna get that number. Very good. So you get 0.2 something. So you have this number, you have everything. The only unknown there is the one that is asked of you. So try to do this in a reverse manner and see if you can calculate and solve this under 2 minutes. That's my my challenge to you guys. And so I'm going to end this this class, and if you want more questions with regards to the periodic table, I'm going to post this Kahoot game as part of a practice for you guys to work on. Okay, so this is what's supposed to be our Kahoot game today, but since we're gonna be running out of time and I do want you guys to watch that video, I'm gonna leave this as a free-for-all thing. So I'm just gonna grade you guys based on your attendance. So dimensional analysis homework assignment. Let's go do that now. Let's take a look at the homework. Are we talking about the which one are we talking about? We're talking about homework. Okay. So we definitely need to go to MyLab and Mastering. We're talking about homework, right? We're not talking about lab. Okay. It's there. Dimensional analysis. For attendance, don't worry, your name is already posted, Ava. So for those who used an iPhone, I have no way of grading you because unless you have to register every time you go to Zoom, make sure you register under your name. It's going to be automatic. Zoom has a way for me to check the analytics. Homework, it looks like for homework, it's already posted. So I'm not sure what you're talking about here, Kendall. Okay, perfect. Yes, so everybody, this is the end. Goodbye. Attendance, no worries. If you have your names here, you're gonna see your scores updated for the discussion. You're gonna see points in there. I just didn't do it yet because I have to export it from Zoom and I have to manually input it to Canvas, but you're gonna see it. If you don't have a score there, please let me know. And then we can always check where you are, okay, with your HTML address. Okay, no more breakout session. Oh, additional help. Yes, of course. After this, feel free to stay and then we're gonna talk about other stuff, okay? Alrighty, and that concludes